Morning, good afternoon, wherever you may be in the day. Thank you as always for choosing my chemistry part of your day. This is the fourth and final component on stoichiometry, at least with dealing with solids. Eventually we'll do it with liquids and gases. Hopefully you can't hear the baby screaming upstairs. And we're going to build on the second out of those four videos, which dealt with theoretical yield. So now we're going to compare that theoretical yield to actual yield. So without further ado, percent yield. Okay, so what is percent yield precisely? It's a percent, so it's 100 times a ratio, and we want the part over the whole. The maximum amount, all the calculations we've been doing are assuming perfect reactions. Not realistic, but it does give us kind of a maximum point of what can be produced. And that's our theoretical yield. So that's going to go on the bottom. As a reminder, this is what we've been calculating. And as a second reminder, if there's more than one reactant, we've got to do the calculation for both, and it's the smaller number we want. And if you've done this correctly, your yield should be between 0 and 100. You can't have more than 100%. I guess if you had impurities, a wet sample, sometimes in the lab you might calculate that, but that tells you something went really wrong. And again, you can't have less than 0. So it's between 0 and 100%. So if you do your calculations right, you always put the small number with the big number. Not a good way to go in case you do make a mistake. And then the experimental yield goes on top. And from a classroom perspective, or a testing perspective, this number is almost always given to you. Why? Because the only way you can get this number is to have it given to you, or you could run a lab. So unless they give you the percentage, this number is the one they give you, and the real problem is to calculate the theoretical yield, just like we did on video 2. Then we do an extra step at the end. Okay, so what would that look like? First I'll give you a little bit non-conventional one, and then I'll give you a conventional one. Or I will just have them all fall on my head. Alright, so let's take this example as it moves around the board on me. Cisplatinum is it's a drug therapy. It's part of a drug therapy for cancer patients, and it's made from the reaction of potassium platinate chlorine plus 2 ammonia, and that gives 2 potassium chlorides in this compound over here. If there's a 95% yield that is obtained from the reaction of 56 grams of K2P2Cl4 and excess ammonia, how much of the cisplatinum would be produced? So again, breaking down word problems. Make sure you have the reaction. This is one piece you would want to have in your notes. And then I like to put the other piece of information of what we know underneath. So I would put 56 grams here. I would put excess here. 95% yield. And we want to know how many grams that would represent. So just so we have those pieces in place. You can see we have no information about this compound specifically. And we do here. So again, this is a clue. Going from compound 1 to compound 2, we're going to have to use a mole-to-mole ratio, and it's going to have to come from a balanced chemical equation. So hopefully you're getting more comfortable with that. It's getting smoother and quicker, and let's jump into that transition right now. Or fall into it if the board's full. Okay, so let's go back. If you're really stuck on where to start on a problem, 2 pieces of advice. One's a little bit sarcastic. If all else fails, convert everything to moles, which is what we're going to do right here. And that is really the starting point. The other thing is always start at the end. It's asking you to get the percent yield for this the amount actually produced, the experimental amount from the reaction. And they gave me a percent yield. So I know the percent yield is the experimental over the theoretical times 100. I know that's 95. I know that's 100. I know I'm trying to find the experimental yield. That's what I've been asked to find. So I just put X there. But unfortunately, if I look in the problem for the theoretical yield, we don't have that, which means we have to calculate it. So we're going to calculate the theoretical yield, then we can get the actual yield out of this relationship. So, going back to what we know. We are only given one piece of information, grams of K2PCl4, and we are asked about the yield of this compound. So that's what we want to solve. Sorry about the color change. And I did this quick so we have them here, the formula weights, so we don't have to spend time in the periodic table. So again, with compound 1, compound 2, we have to use a mole-to-mole ratio, which means step number 1 is get it to moles. Do we have a relationship between grams and moles? Absolutely. Formula weight. And it's always a whole bunch of grams per 1 mole. Ooh, sorry about that, that's terrible. Then we can use our mole-to-mole ratio, which in this case is just 1 to 1. So that's pretty straightforward. And terrible board spacing. We're just going to continue this out then. And then lastly, the formula weight of the other compound. We want moles to grams. And then we have that weight up here somewhere, 300. And again, this represents, so we're going from reactant to product. Remember what this represents. This is the maximum amount of product we can make from that much reactant, or our theoretical yield. So again, multiply across all the tops. Hopefully you're getting very comfortable with these types of calculations. Divide all the bottoms. And I get 40.48. And we should ask ourselves, is that reasonable? Well, if we start with 56 grams of this and some of it breaks off and we have 40 left, sure, that's reasonable. It's ballpark. Again, when you get an answer, you don't have to know that it's right, but just make sure it's not really wrong. And that's reasonable. So let's run with that. And that's my theoretical yield. So we can plug that in here. So we know it's 95% is 100 times the experiment over 40.48. Solve for our experimental yield. Multiply both sides by 40. And we get 38.5 grams as our actual yield. So again, all I did to solve this was multiply by 40, divide by 100, and solve for the top of the fraction. Or you can cross multiply and do the same thing. You get 38.5 grams. So hopefully this is pretty straightforward. This is a little bit trickier, although the calculation, this part I think is pretty straightforward. And it's the same chunk we've done for all of the calculations in all the videos. This is a little bit more of a traditional version of this problem. And I've changed the units up just a little bit, just to make sure you're paying attention and you're reading and thinking. Don't memorize process. I'll change up how I do this. I'm not going to do it the exact same way every time. Think about what you're doing. Don't just memorize processes. If I can get the board not to fall on me, I might even work the problem. Thank you. Okay, so ammonia is produced from the reaction of hydrogen gas and nitrogen gas to form ammonia. If we start with 4.5 moles of hydrogen, 2 moles of nitrogen, and we react that to get 8.2 grams of ammonia, what would be the percent yield? Very standard worded, very traditional problem here. Again, if you want to take the reaction and divvy things up, I think that's helpful. 4.5 moles, 2 moles, 18.2 grams, and we want to know the actual, we want to know the percent yield. Percent yield's got to be a product. There's only one product, so they must be talking about this. So again, we could convert this to something, but remember, for a percent yield, we need both the experimental value and the theoretical value. We don't have both, so we're going to have to calculate one. And remember, the one that we calculate is the bottom. So we're going to calculate that. The theoretical yield. The experimental yield is what's given to us. And you may get to see this fall on my head yet. So this is given. Again, why is it given? Because you have to get it out of a lab. There's no way to predict what it would be. It's an experimental value. So that's going to be given to us, and that's our 18.2 grams. The real question is, what's the theoretical yield? Well, we have two other numbers we could use to calculate over. And again, we're going from chemical A to chemical B, which means we have to use a mole-to-mole ratio, which means step number one is get our answer into moles. Second question is, which one of those do we use? Well, if you're really good with numbers, you probably know which one it is. But I'm going to pretend I'm not good with numbers, and then we can do both calculations and see which one matters. So, first step is what? Get everything into moles. People will make this mistake. Don't fall for this trap. What unit do we have right now? Moles. Do we need to use the formula weight? Do we need to do anything with that, or can we jump straight into the mole-to-mole ratio? Sure, let's jump straight into that mole-to-mole ratio. Good thinking. So moles of H is on top, moles on the bottom. We want ammonia on top. Ammonia on top. And again, we just take these numbers straight from here and we keep them with the same compounds. So this stays 2, this stays 3. I'm really out of practice doing this. And on the other side, why won't you stay? I apologize for the crazy board work. There, I think I got it now. And we're going to do the same thing down here. We got moles of N2. Moles of NH3, And then since our problem is in grams, we probably want our answer to be in grams too. If we just need the limiting reactant, we could stop at this point and take the smaller number. But let's do that last step. And go through and calculate those numbers. $51.1 and 68.2. Again, it's the smaller number we want. So the larger number we're going to get rid of. This is an excess. This is our limiting reactant. And this is the number we'll use. This is our actual theoretical yield. So again, just to put in perspective what those numbers mean. Once we find the larger number, we can get rid of it, and that's an excess, and it really doesn't mean anything. The one that's the smaller number, that's our theoretical yield, and whatever we started with, that's our limiting reactant. Now we have that number. We just put it here, 51.1 grams. Take our 18 over the 51 times 100, and that should be like 20%-ish. And I get 35.6, so clearly not 31-ish, but we're close enough. And that's a reasonable percentage. Anything really between 100 and 0. There are reactions where 1% is wonderful. There's reactions where 99% is okay. And you'd have everything in between. So that's it. That's percent yield in a nutshell. Hopefully this was helpful. I did 2 different examples, and that's really all you need to be able to do and reproduce in a test. Again, it's using the same skills, just in a slightly modified way, bringing in that actual data. And that actual data is given to you in the word problem, or you'd have to work in a lab. And obviously on a test, we're not going to ask you to go to a lab, run an experiment, run back with your data, and then do the calculations. So that part's going to be given to you on a test, just common sense-wise, and in the book. Thank you for your time. Look forward to seeing you in class. Hope you're doing well.